Okay, so Matteo,
Can you see the slides?
yes, we can. So please, the screen is yours.
Okay, thanks a lot. Okay, so today we'll tell you about some work I've done in collaboration with Alberto Castellano from the University of Chicago. And if I have time at the end, also about some work in progress with, again, Alberto, but also Dieter Lust and Carmine Montella from Max Planck Institute. So the motivation for this work started with a question. And well, to phrase this question, let's just consider an effective field theory. And we know that quantum effects can be incorporated in the form of higher derivative corrections. And usually these higher derivatives, being like higher ordering derivatives, must be suppressed by a certain cutoff scale. And the kind of cutoff scale you have will depend essentially on the effect that generated higher derivative term. And if, for instance, you consider like a compactification, the cutoff scale that will appear will be nothing but the Kaluza-Klein scale, which essentially is the mass scale of the tower of kicking modes you have integrated out. So the question is, okay, in this last example, in which you have like a series of high derivative corrections governed by this Kaluza-Klein scale, we were wondering what happens when like you reach that scale. Well, actually, we know the answer. Essentially, the EFT is breaking down, but not completely, because still there is an EFT description, because the theory reorganizes itself in a higher dimensional effective field theory. And you have a sort of phase transition. So our question was, okay, suppose that we take a stable object, which is like protected, how this object would experience this phase transition? Because our intuition will be the following, that if this object is kind of an embedding well defined at the level, already at the classical level in both the lower dimensional theory and higher dimensional theory, and it is well protected, like for instance, a BPS black hole or a BPS, well, a black brain, probably could be that this object could survive the phase transition, and we can talk about the physics of this object even beyond the breaking down of the effective field theory. So we can make computation for an object which in principle is an EFT solution and try to see if its physics is surviving beyond the breaking of the EFT. So at the Kaluza-Klein scale or beyond. And concretely, what we have done to test this was looking at the simplest non-trivial example you can think about, which is we took BPS black holes in 4D n equal 2 with a large volume approximation. And essentially, in this setup, what we've done was trying to like take a black hole and try to see what happens if we decompactify it in 5D. And to do so, therefore, we have to essentially add all the quantum effects relevant for this decompactification, hoping that, and what we were curious about is seeing how these quantum effects modify the entropy and how, I mean, this modification behaves when you reach the EFT transition. And remarkably, even if these corrections are well known, I think no one in the literature, to the best of our knowledge, that's why we put out this paper, realized that actually all the perturbative one loop effects due to integration out of the zero resum in a way which is finite at all order in this flow from 4D to 5D. And on top of that, you can also add non-perturbative effects and verify, well, you compute that with resurgent techniques, and you can verify they don't spoil your result. And to have a better well, intuition of what we are thinking about when I'm making all these statements, just consider a family of black hole solutions, which starts with a large black hole, large with respect to M-theory circle in 4D. And then we are like, it's a one parameter family, and then we are shrinking these black holes till the regime in which it is at the same size. I mean, the horizon of the black hole is the same size of the internal circle. And then we go beyond and we reach the regime in which it is much smaller than M-theory circle. And our intuition is that at the beginning, we are visiting purely for the effective field theory regime. Then we are in this phase transition regime. And then we end up in a purely 5-dimensional regime. So unless there are questions, this is essentially what we are going to look at. And well, brief outline, we start with a brief review, then looking at this main example, which is this explicit gluing from 4D to 5D, Then the 5D object will be a black string. And in part 3, we will essentially look at what is special of the black string and what can be instead generalized to other systems. And then again, if I have time, I will give you some insight on current work. So really, really fast. We work with for d n equal to theory. This is the action at the two derivative level. We have in blue the vector multiple sector and in gray the hypermultiple sector. In this work, we will assume that we can truncate the hypermultiple sector. And as you know, the vector multiple sector essentially is expressed in terms of a quantity called prepotential, which completely determines the physics. And the reason is that if you look at the action, the blue piece, you have these kinetic matrices. And if you then look at the equation in the bottom of the slides, you see that all these kinetic matrices are fixed in terms of a single purely f function, which is what is the two derivative prepotential. Now, what you may not know is that this theory admit deformations in terms of supersymmetric BPS operators containing high derivatives. Here on the left-hand side, I wrote down the off-shell formulation of this huge class of operators. And the right-hand side, I just opened them up, like writing the same operation in terms of components. And all what you have to know about this class of operators is that for explicit embedding in string theory, these calligraphic FG functions are holomorphic functions that can be fixed in terms of topological string theory amplitudes. And all the effects of these terms at the level of the effective field theory can be just condensed in the notion of a generalized prepotential, which is the thing I'm writing here. Can you see my mouse? Just to check. Okay, perfect. So why we call these? Why do people call these general prepotential? Essentially because using this quantity together with some other scale quantities, one can still have in this modified theory all the nice properties we love about for the n equal to a two derivative. We have a tractor mechanism, we have simple expression for BPS black hole solution, and so on. And all these, all the relations that all in for the n equal to a two derivative can be still written in a way which is reminiscent of the two derivative language with these generalized quantities. So we have here in the first block, I will just let you notice that we have this YA, which are a scale version of the scalars on the vector multiplet. They usually called X in the literature. And then we have this calligraphic Z, which is, again, a scale quantity of the central charge. And this F is this general prepotential. And you see that when you write down the vector mechanism, it looks really like the tractor mechanisms you have like in the two derivative level, just with these generalized quantities, where P are the magnetic charge of the black hole and Qs are the electric charges. And for BPS black holes, the linear isometric is governed by this quantity calligraphic Z, which is again this generalized central charge. And for this class of black hole solution, people computed entropy formula, essentially the world entropy for this class of solutions, which can be written in a really nice and compact form, as shown in the last equation. Now, last piece of information I need to remind you for this review part is that I say that we are working in the large volume approximation, which means that we are assuming that the prepotential can have this generic structure, which holds independently of the Calabi-Yau manifold we are compactifying on. Because whenever I'm saying that we are working with for the n equal to, what I really mean is that we are thinking to work in type IIA compactifying a Calabi-Yau. And when I say that we are decompactifying to 5D, I'm thinking of M theory on the Calabi-Yau. Again, we are in the large volume approximation, so the Calabi-Yau don't play any role. The integration out of the K modes of Calabi-Yau don't play any role. But still, I mean, we have some information of which is the Calabi-Yau we started with, because we have this capital D and small d, which carry the topological information of the Calabi-Yau. Now, this G term usually is something a little less common to see in the form of the prepotential, and it's essentially a term due to higher genus corrections. So this is genus 1 corrections, this is 3-level, and this is higher genus, essentially. It's a little bit more subtle than this, but as a first order, this is a good explanation. And the leading order correction of this higher genus term can be written in the form of an asymptotic expansion in terms of, a parameter alpha, which is our perturbative parameter. Here you can find its definition. And well, the powers are nothing but the powers in the genus number. So if there are questions, otherwise, let's go with the main example. So let's start with the BPS black holes with D0, D2, D4 charge, or even better, without D6 charge. You can find the solution to the tractor equation at the two derivative level, just like well, solving a tractor equation, and the solution read this way. And then you can just take the entropy formula I showed you before, well, specialize in the two derivative case, replace the solution, and you get this kind of expression, which is really, really common. You have this electric charge, Q0, which is a combination of D0, D2 charge, and then you have this cubic piece in the magnetic charge set with the D4 charge. So what is interesting of this class of solution and this two derivative, well, we found the two derivative level, is that we may ask when this solution are actually within our large volume approximation. And to ask this question, we can just look at which is the value of the volume of the internal Calabi-Yau and the suctions at the horizon of the black hole. And what we find out is that this family of D0, D2, D4 solutions can organize actually in something which is a one-parameter family, because essentially we can be within the large volume approximation having this ratio, which is essentially arbitrary, because we don't need to fix this ratio to stay within the large volume approximation, which means that we, at the two derivative level, we have like a one parameter family of solution with no D6 charge, which are lying within the large volume, approximation. And the most important thing to notice is that moving in this family of solution is equivalent to like changing this ratio, is actually equivalent to change the value of Y0. Now, remember this, we have an entire one-dimensional, one-parameter family of solution without D6 charge, in which we can, well, move on, just changing the value of Y0. Now, let's add quantum corrections. The tractor equation gets modified, and the solution gets modified. Here in blue is the modification, and as a consequence of this, we also have a modification of the entropy, whose perturbative correction can be like essentially, which we can expand in the perturbative parameter, and we have like the leading order correction is this blue piece. Now, as you may remember from these slides, this G term is expanded in this alpha parameter, and this alpha parameter is related to 1 over Y0. You see this relation, just the definition. So what we find out is that this 1 over Y0 not only is the parameter of this one parameter family class of black hole solutions, but is also related with the perturbative parameter, which we are using to expand the quantum corrections. We are including like integrating out the zero branes. On top of this, if this is not like nice enough to make this like combination special, we also have a really nice geometric interpretation of what is this parameter. Essentially, one can rewrite this alpha as the ratio of the inverse Kaluza-Klein the zero scale, mass scale, and the black hole horizon. So essentially, we can really give like a visualization of all these pictures, saying that we have a one parameter family represented by this black line in one side of the arrow, where the value for which alpha is much smaller than 1, which means Y0 is much bigger, well, is much bigger than 1. And the black hole has a radius which is much bigger than the internal anterior circle. And it's also the same scale in which the perturbative correction are suppressed because the perturbative parameter is small. Then when we are moving in this family, we are shrinking the black hole with respect to the anterior circle radius. And when the black hole is at the same size of the internal circle, essentially also this expansion parameter is order 1, signaling the breaking of the perturbative expansion of the effective field theory. And finally, when the black hole well, alpha is much bigger than 1, and so the infinite series of correction is completely exploded and anything doesn't make any sense. But like from a geometric perspective, what we're doing essentially considering the black hole to be much, much, much smaller than the M-theory circle, essentially decompactifying. And so like approximating the black hole to be a black string. So this is like, again, this is the same picture there was at the very beginning in the second slide, but this is what we are doing essentially. We are taking this one parameter family of solution, we are moving along it, geometrically we are shrinking the black hole, and at the same time, this shrinking of the black hole can be seen at the level of the correction from the point of view of making large the perturbative parameter. And now the question is, okay, sounds good. This is a really qualitative like description of what is going on, but can we test this? Can we be explicit in checking this? Well, actually the answer is yes. We can compute the entropy and see that we can literally start with like the black hole entropy and obtain the black string entropy in this limit of alpha going to infinity. So a little bit of computation. What we've done, essentially here, I'm summarizing all what we've done. First of all, we took the gamma curve alpha topological free energy to approximate, well, to represent this effect of having like D0 brane integrated out. Then, well, to evaluate this calligraphic I integral, what you have to do is essentially split in positive and negative mode, change of coordinates. And then what we are doing is taking these negative modes and deform the contour of integration. Deforming the contour, you will end up with picking up some residue or some poles and having like a line integral only now on the positive axis. So what it turns out is that the line integral can be again massaged by a Borel resummation, and you get like a finite contribution, and the poles can be like evaluated just using residue theorem. And these poles will give a non-perturbative effects, and this line integral, once you Borel resum it, is giving you perturbative effects. All this interpretation is nice, but let me just point out that an alternative method is also like combining these two components into a nice contour integral. And for a really detailed and clear independent derivation of all these like ideas and all these picture of like writing things as a contour integral, I invite you to see the nice notes of Eran and Jack in a tab. So, which is the result of doing all what I told you? We have a perturbative piece and a non-perturbative piece. Notice that these two pieces, despite the infinite sum, are finite for every value of alpha. On top of it, the perturbative piece is purely real, and the non-perturbative piece is purely imaginary, which means that the non-perturbative piece, given that all what enters in the entropy is the real part of the calligraphic E integral, that's because actually what enters is the imaginary part of G, but there is an extra I, so what you have to pick is the real part of calligraphic I. It's only the perturbative piece which is entering in the entropy for these black holes. And these black strings are completely insensible to these non-perturbative effects. And if you just try to plot what is this calligraphic P, to have like a better understanding of how this function is going, essentially you find a monotonic function which is going to 0 when you take alpha large. Essentially, these perturbative effects are diluted the moment in which you take the compactification limit, which essentially means alpha large, because I call you that alpha large means that you're shrinking the black hole to be much smaller than the Matteo circle. And the main result is that now you plug everything into the entropy formula. This is the entropy for a generic D0, D2, D4, valid within the large volume approximation. And if you take the limit for alpha large, all this entropy is exactly the precise entropy of the black string. And well, this entropy of the black string is exact because it has been computed by several methods, like via microstate counting, or also via macroscopic consideration, using the fact that the 5D n equal 1 theory is protected in its high derivative terms. But this is like, I think, really amazing. Like, we are doing all this procedure and we're exactly seeing in a quantitative and precise way that we can do a purely 4D computation, reach the phase transition, which the 4D theory is completely broken, and actually go beyond it and really reach the purely five-dimensional regime, and still everything makes sense. Everything like cancel out, combines, everything is tamed, and the entropy survives beyond, the physical solution survives beyond the breaking down of the EFT, the four-dimensional EFT description. So I guess I have more than 5 minutes, even that I haven't received any alert. So
You
now I'm
have around 5 minutes.
Okay, perfect. So part 3, what is general, what is special of the black string? Now, we look in the paper also to the D2D6 system, still like this G term of the prepotential, so the homogeneous term is organized in powers of this alpha parameter, actually the modulus of alpha. And this modulus of alpha has the same interpretation, like ratio among the D0 scale, so the inverse of the D0 mass scale, and the black hole horizon size. And again, also in this case, one can like evaluate these effects looking at the Schwinger integral, and the Schwinger integral is, well, resum into a finite object, which is finite for all values of alpha. Now, there are still some differences with respect to the black string. Essentially, first of all, when you have D6 charge, alpha is not anymore, well, completely free. Actually, it's upper bounded, which means that we cannot really take anymore the decompactification limit to 5D. We can still reach the phase transition regime when we hit the KK scale, but we cannot cross the KK scale. But actually, I mean, I think that this is not really surprising, because essentially the family of solution we are using to explore this limit is a family of solution that exists already classically, and already classically there is like a topological obstruction to like going beyond the KK scale, because like the minimal black holes are the KK size, and the reason is that essentially that in 5D this solution uplifts to solution with tau-NAT charge, so a topological charge, and you cannot like decompactify and preserve this charge, because otherwise you will like destroy the topological charge itself if you remove the S1 topology. Another thing we observe in this D2D6 is that the still we can use our method, the one I commented, to like evaluate this integral, but the contouring representation is broken down. But well, we may ask, okay, again, what is special of D2D6 and what is the general of general BFP solution? What we can do is just looking at the most general case. This is not published work. This is work in progress with Dieter, and is going to appear soon. We can actually compute the entropy for the most general black hole solution with all the charges from D0 to D6. We can see that in this case, actually that contour integral prescription is still working. So actually the breaking down of the contour integral is something specific of the D2D6 setup. And it's essentially due to this alpha parameter being purely imaginary. And instead, looking at this general system, we can see that non-perturbative effects, which means non-perturbative poles picked up by this contour integral, do contribute always to the entropy. So the turning off of the non-perturbative effects is something special of the black string. And again, looking at this black hole solution, at least as long as we want to stay both in the classical approximation, so if we want these black holes to exist also classically, and we want to be within large volume approximation and moving only in the vector multiplets and not considering hypermultiplets, we are finding that we are not able to explore different infinite distance limits. We only have this decompactification to 5D. Now, conclusions. So just to a brief summary, what we find out is that we show that it's possible to resum the one loop effect to D0 branes, and also taking into account the periproduction effects. And the resulting correction to the entropy are valid also beyond the validity of the effective field theory, in which we computed them at the very beginning. And then we also show that it is really possible to, like, in these scenarios, taking like family of black hole solution and really glue a purely four-dimensional object to a purely five-dimensional object. And this gluing is surviving, again, the phase transition among EFTs. So the physical solution is, in a sense, more fundamental than the EFT description itself. Nothing surprising, but at the same time, I mean, it's non-trivial to see this explicitly with a solution which is like stable and so on. Then We also show that, like in some cases, I mean, all what we found is that are the compactification of 5D, but we also saw that it is not possible sometimes to like cross we can reach the transition regime always, but it's not always possible to cross it when there are topological abstraction due to the existence of like a classical solution, which like, to exist requires that a non-trivial topology, which essentially can be rephrased in the form that the classical solution has a minimal black hole, which cannot be smaller than the KK scale. And then also we saw that non-perturbative effects turn off in the case of the black string, and this is special of the black string. Once I say non-perturbative effects, I'm thinking about like pair production of D0 branes. And this is, well, the technical way in which it happens, because essentially the poles give a purely imaginary contribution, and the entropy is washing out this purely imaginary contribution part. And well, to conclude, some future direction and things we are thinking about and we are working on, again with Dieter, Alberto, and Carmine. We want to try to see what if can do something like exploring a phase transition, not like a decompactification, but an emergent string limit. We think that this can be doable. We have some example in mind. That we want also to look at like D0, D2 contribution to start looking at F-theory scenarios. We want to look at small black holes instead of large classical black holes, because one of the assumptions was of all this work is working into black holes which exist already at the classical level. So small black holes, well, physics of small black holes cannot be directly argued from our results. And finally, we were interested like to just study in general the stability of non-BPS black holes and where these Schwinger effects turn on, turn off beyond like these BPS examples. And that's all. Thank you a lot for the attention.
Thanks, Matteo, for the very nice talk. So now there's time for people to ask questions. I see the first one is by Alex, so go ahead.
Thank you. Thank you, Matteo. It was a very nice talk. And it's really cool that you can do this resummation and see the entropy matching. So there's a series of works by Green and Van Hoof. I don't know if you're familiar with them, but what they show is that if you take the lower dimensional massless threshold, like from loop contribution, and then if you take the KK contribution and the loops, you can Borel resum them to get the higher dimensional massless threshold. So I think it might be like a similar story. They do it in a lot of different corners for M theory and string theory. They don't, I mean, the concern there is not to reproduce the black hole entropy, but is to show that you can really like recover the coefficient of the higher dimensional EFT on the nose with this Borel resummation. So it might be something related to that.
I think that in a sense is what we're finding, no? Because, well, in a sense that what we are seeing is that when we take the 5D limit, I mean, all the correction we know that are not there in 5D are going to be killed. But I mean,
right.
I mean, thanks a lot for the reference. I mean, I definitely want to
so
look
there
at that.
there are these like there might be like 10 papers or something like that.
Okay.
And we also reference them in the appendix of our paper, the Tale of Three Scales. And so another related comment is a lot of times, you know, people say that, oh, the effective field theory breaks down at the KK scale because there are these higher derivative corrections and the scale of them are controlled by the KK scale. So the thing is that, go ahead.
Yeah, I mean, my precise statement is that it's not that the EFT breaks down, but what I said is that there is a phase transition and you can reorganize it into an higher dimensional IFT. This is my exact statement.
I see. Yeah, I agree with that. But I just want to clarify one thing. So there are two ways that people define EFT. One way is to remove the lower dimensional massless threshold, then you're left with this KK controlled coefficient. But then if you include the lower dimensional massless threshold, when you're 2IR, when you're below the KK scale, that's more important. And when you're much above the KK scale, all of the KK particles sum up to give you the higher dimensional Planck scale. So in some sense, you know, exactly what you're saying happens in that The KK particles don't really show up as the thing that controls the higher derivative correction, but there is this transition where you go from the lower dimensional massless threshold to the higher dimensional mass threshold, and it happens exactly around the KK scale. Yeah, but I mean, this is something we also, talk about it in our appendix if you want to have a closer look. But yeah, thank you.
And this happens like completely independently of any supersymmetry argument.
Yeah, so you can just, if you consider the KK tower for n, generic this decompactification limit, you can show that the scaling of it works. But this series of papers that I was talking about, they take supersymmetric constructions just to show that like the numbers exactly work. That you can Borel resum the KK contributions with the lower dimensional massless loops because ordinarily it would be divergent, but then you can Borel resum it to get the higher dimensional coefficient on the nose. But there is also kind of a more general argument that the scaling of it works. Yeah. I'm also happy to talk about it later if you want.
And just by curiosity, if there are no other one as questions, there are also like contribution due to like non-perturbative effects in these, because essentially with Borel resummation we are obtaining the perturbative piece, but to pick the non-perturbative piece we are still have to like look at the residues which are scaling with one of perturbative piece is giving you the behavior which is scaling with alpha. But non-perturbative piece scaling as 1 over alpha, they're not really picked by this Borel resummation, but they're picked by like literally modifying contour integrals and like evaluating them with residues theorems, picking up balls. So you're saying that it's just a matter of Borel resummation and there are no non-perturbative effects playing a role there.
So here, if I'm not mistaken, I think the claim is that by Borel resumming the perturbative pieces, you can get the higher dimensional perturbative quantum correction to the EFT. Yeah. And in the decompactification limit, you would expect the perturbative contribution of let's say the KK particles to be the dominant piece.
But there is non-discussion. But they also discuss non-perturbative effects, or they don't play a role in this.
I'm not sure. Okay. I'm not sure.
Okay, cool.
Yeah.
Well, thanks a lot for the reference.
Perhaps I can try to answer that question.
Yeah.
Just to comment, no, there are no non-perturbative effects there. Like literally what you are seeing is that from the higher dimensional perspective, the massless threshold is just running a loop of a massless particle in higher D, right? Once you integrate out the Kaluza-Klein, this becomes a three-level effect that comes from a higher curvature term. So then you just know that by the UV completion of the theory, these higher curvatures must resum to the higher dimensional threshold, which is a one-loop effect. So there are no non-perturbative effects there.
Yeah.
Okay, thanks.
Thanks, Jose.
Okay, so thanks for the very nice question. I think we can close here the first round of questions for Matteo and give him now also an applause. And okay, I'm gonna finish